People in the back hear me? Okay, great. So please get yourself seated. So TA just posted the exam grades on Canvas, so you should be able to see it right now. So today we will first finish our lecture on thermal review, and after that we're gonna spend some time to discuss the exam, and we will go over some exam problems that has the most mistakes, and we will answer any questions you might have. Okay. So last week we started to review thermodynamics, and we talked about the equilibrium of a system, and we talk about at a system level. First of all, like equilibrium deal with system states, right? It doesn't tell us how do we get from one state to another. Second of all, at equilibrium, there's no macroscopic change, and from the energy point of view, the condition for equilibrium is that the energy of the system is minimized. So that conceptually is good for us to understand equilibrium, but it's not that useful when it comes to deal with a multi-phase, multi-component system. So we spent some time kind of derive the conditions for equilibrium for a closed multi-component, multi-phase system. And at equilibrium, the condition says the temperature and the pressure of each phase is equal. In addition to that, the chemical potential of any species in each phase is equal. Okay, so that's kind of the condition for equilibrium. But a lot of times, chemical potential is really not the best thermodynamic quantity to use. So that's why we define some other thermodynamic quantities, including fugacity and activity, right? Since both fugacity and activity, they are monotonic function of chemical potential, which means at equilibrium, when you have chemical potential of any species to be equal in all phases, then you should also have fugacity and activity of any species to be the same in all phases, right? So based on that, we kind of apply that condition to a simple liquid vapor two-phase system, and we can derive basically from the if we set the fugacity of a species I in both liquid and vapor phase to be the same, then we can derive an equation that relates the ratio of the mole fraction of species I in the vapor phase to the mole fraction of the same species in the liquid phase. We can relate this ratio to the fugacity coefficient as well as activity, right? And this ratio is basically, this ratio is a very important parameter, which is called K-value. And the physical meaning of this K-value is that it tells us how much, for a liquid vapor phase equilibrium system, it tells us how much one chemical species wants to stay in the vapor phase compared to in the liquid phase, right? The larger K-value is, right, this species wants to, stay in the liquid phase more, vapor phase more, right? In other words, K-value is kind of like tell us how volatile this, this species is, okay? And when we have multiple species in one phase, right, then depending on the relative, the relative K-value, which in here we define as a relative volatility, that's kind of a ratio of the K-value of species I versus species J. These tell us in a relative sense which one of the two species is more volatile, okay? And when it comes to separation, if we are trying to, separate two species by creating a new phase, right? From, in this case, we're creating a vapor phase from a liquid mixture, or we by evaporation, or we condense a liquid phase from a vapor mixture, right? And whether or not we can really separate these two species depends on the relative volatility. And as long as the relative volatility is much distant from one, either it's much larger than one or it's much smaller than one, we can relatively easy to separate these two species, right? We will revisit this in our next lecture in single stage separation. But now, for this lecture, we kind of focus on key value because we're going to use this key value later in our course. We need to know how it is defined, what its physical meaning is, and how can we find it, right? So there are many different equations we can use to compute key value. There are rigorous forms which is derived from the equations, right? The definition of the key value we just shown. Here, this is kind of definition, the key value, not the definition. This is like the definition of key value is y over xi. But for a liquid vapor phase equilibrium, right, from equilibrium condition, we can derive ki to be equal to the fugacity coefficient in the liquid phase divided by the fugacity coefficient in the vapor phase, right? And we can use equation of state to compute the fugacity coefficient, right, which we'll talk about in our next slide. And there are different equations of states, right? For example, the BWRS, SRK, or PR equation states we can use. And we can also compute Ki based on the activity coefficient and the fugacity coefficient, right? There are also approximate forms, which are basically simplification of these two rigorous forms under certain assumptions. The first one that's most commonly used is the Raoult's law, which applies to ideal mixture, right? Which says the key value is the ratio of the saturation pressure divided by the pressure. Okay. Then there's a modified Raoult's law in which we multiply this ratio with activity, with activity coefficient. That which the activity coefficient here is used to deal with the non-ideality, the deviation from ideal mixture. Then there's Poynting correction or Henry's law. In a real problem, you could have many different, in each phase, you could have many components, many different species, and you can mix and match for different species in a mixture, which is to say that, let's say if you have two components in your liquid mixture, so you can use Raoult's law for one to compute key value for one species, and you can use Henry's law, for example, to compute the key value for the other species. You can use them, right? Now, Raoult's law says the key value is the ratio of the saturation pressure divided by pressure. Okay, how it is derived? So to derive Raoult's law, we can look at if you look at the ideal mixture of gases, and we know the partial pressure of a component I is proportional to its mole fraction multiplied by the total pressure. That's a Dalton's law. Then for an ideal liquid mixture, the pressure generated by each of one of the component I is proportional to the mole fraction of I in the liquid mixture multiplied by the saturation pressure of this species I. Okay. So then if we set this 2p equal, right, then you will have equation that link these two terms, and then if you rearrange the terms and then you will have y over xi equals pis over p. That's how we get Raoult's law. Okay. But as you can see here, the derivation process relies on the assumption that both the gas, both the vapor and the liquid phase are ideal mixture. Okay. When the mixture is non-ideal, then we can apply, one modification we can apply is that we can apply activity coefficient just to deal with, account for this non-ideality factor. Okay. So the saturation pressure, which is the vapor pressure for each species, can be computed using the Antoine's equation, which says the log of the pressure is a function of, is dependent on 1/T in this kind of a linear format, right? And this equation is plotted in this figure where we have vapor pressure. This is in the log scale, and the temperature also on a log scale. Right? You can see that they are kind of linear in this figure. Right? So for Raoult's law, as you can see here, that Ki is only dependent on saturation pressure, which depends on temperature in an exponential manner, but does not depend on composition, right? Which is a huge assumption. Now, in the older times when, for the Raoult's law, you can use a computer, right, to give the parameters for the Antoine's equation, then you can compute the K value at any temperature for a given species. But in the older times in which we don't have computers, or computers are not powerful enough, a lot of times engineers has to use graphical methods to get the K value, which is basically this graph is like a table, right? It's like a table in which you have all the values for a lot of different chemical species, right? But in a graphical manner. And we can get the K value from this graph. Let's see, how do we read and use this figure? First of all, there are several axes in this figure, and if we look from the bottom to the top, the bottom one is the normal point axis, right? With the unit is degree Fahrenheit, and so this gives us the different chemical species that with different boiling temperature from low to high. So then there's a second axis here that is K value axis, right? On a log scale, and from left to right, you go from low to high. Then here you have a like a skewed partition coordinates where you have two axes, right? Here on the left, you have the pressure in PSIA. On logs, this is also on log scale, but from big to small, right? From along this axis, you go this, right? Then on the right here, you have temperature in Fahrenheit, from low to high. Okay, so how do we use this figure? For example, if we want to find out the K value of propane and isopentane at a temperature of 60 Fahrenheit and 1 atmosphere pressure, first thing we do is locate the temperature and pressure on this map, right? So 1 atmosphere, that's like 14.7 PSIA. That gives us this dashed line here. Then we have 60 Fahrenheit. That's here, right? Then that gives us this circle. Okay. Then we find out the propane on the normal boiling temperature axis, which is here. Okay. So hold on for a sec. My computer just jammed. Okay, so you have propane here. And you have isopropane here. Okay. Now what you need to do is just draw a straight line between the propane here to the point where where the temperature and pressure sits. This straight line will intersect with the key value axis. And this intercept is where you can read off the key value of propane. In this case, it's 7 for propane and 0.64 for isopentane. And this is useful when you don't have access to computer. For example, when you do homework or when you do exam problems. Okay. Then there's another way to get to the key value, which is called a de Priester chart correlation, where you have like three sets of axes. The left one gives you the pressure, and the right one gives you the temperature, and all the axes in the middle gives you the key value for different chemical species. And in order to find the key value of one component, you need to first identify the pressure and the temperature. Second, you draw a line. Right? For example, if you are interested in the key value of methane at 150 kPa and 100 degrees C, right? What you need to do is draw a straight line connecting this. We have 1 point here, 1 point here. Okay. So what you need to do is just draw a straight line connecting these two. Sorry, that line is not very straight, but you get the point, right? So you get this line, and this line will cross the methane key value axis of methane. Then you can read off the key value at this point. Then there's an empirical correlation to compute key value based on the de Priester chart, de Priester correlation, in which the key value, as you can see here, is a function of both temperature and pressure, right? And for some common chemical species, the key value, the parameters A1 to A3, B1 to B3 are listed in this table. Then if we run out of if we cannot find the key values in those charts, then what we can still do is use the rigorous form of the key value to compute the key value, right? But to do that, we have to start from the thermodynamic equation of states. So here, in order to compute fugacity coefficient, we can apply this equation. That's from your textbook 2.5.2. So here, to compute fugacity coefficient, we can do an integral over pressure, right? By this, here, V is a molar volume, like the lowercase v is a molar volume, then we have R, temperature, pressure. So here, this V at the subscript of the phi refers to the vapor phase, whereas in this equation, this V here, that's the volume. Okay. So you can do the integral with respect to molar volume as well, but now you have to include compressibility factor. Okay. And we can get the compressibility factor from the RK or SRK equation state. So here, from this equation, you can get Z. And the AB are two parameters which you can compute using this and this equation. And the capital the big A depends on small a, and big B depends on small b, and the small a depends on the mole fraction and the small a of each species. And small b depends on the mole fraction and the small b of each species. Okay, and then the small a and the b depends on which equation of state you use. For RK equation of state, A and B, small a and b, they are a function of the critical temperature and pressure of your chemical species. They are related to the critical temperature pressure by this equation. And for SRK equation of state, which is much better in terms of like computing key value, we, in addition to A and B, we also have F omega that depends on omega, which is the eccentric factor. Okay. Now, if you from this you can get Z, and you can plug it back into this equation and do the integral, then you should be able to get the fugacity coefficient and partial fugacity coefficient. Then you can plug it in the rigorous form of the key value. Then you can compute the key value. Okay. Okay. And this figure basically shows the key value of several chemical species as a function of pressure. And in this case, the figure compares the experimental data with the key value that's obtained from the SRK correlation, we just derived. And as you can see, the SRK correlation shows very good, is very consistent with experimental results, right? This is to confirm that SRK equation of state is a very good approximation for us to compute the fugacity coefficient and to compute a key value. Okay. Okay, that concludes our thermodynamics review. Any questions? Maybe it's time for me to update my gear. This is too slow. Okay. So next, let me pull up the statistics of the exam. Okay. So, well, let's first look at the statistics. Now you have your number, so I just want to show you the statistics so you get a sense about where you are and how well you're doing in a relative sense and compared to your peers, and then maybe you can adjust your study strategies in the next part of our course. So we just finished like 1/4 of the cost content, and let me move this. So total points of this exam is 31, and we have max score to be 30 and minimum score to be 13, and the average is 22.5. And we have median to be 23. That's quite close to the average. And the 90 percentile is 27. That means if your grade is above 27, that means your performance in this exam is among the top 10% of all the students, right? And 80 percentile is 26. 60 percentile is 24, and 50 percentile, or the median is 23, 40 percentile is 22, 20 percentile is 20, 10 percentile is 17.5. Okay. So that's just some statistics. Now, let's look at another statistics. So those of you whose grade is above 80% of the total grade, which is 24.8, right? That's 31 multiplied by 8.8, that's 24.8. There's 19 students whose grade is above 80, right? If you belong this group, good work. Please keep up the good work in the next part of our course. And if your grade is between 60% and 80% of the total grade, that is to say 18.6 to 24.8, there's 36 students whose grade is falling into this region. Please go to the TA office hour more often. I think you will do better if you do, if you talk to the TA more often, or if you, work with your peers more and discuss the homework problems. If your grade is below 60%, that is to say below 18.6, and I'm concerned because in order to pass this course, so you have to get at least your letter grade has to be D, and your overall grade needs to be at least 60, right? So if you don't do well in the exam one, that's fine. We have 3 more midterms and we have a final. There's still plenty of time. You can just make efforts to reverse this trend. But please come to my office hour, or at least send me an email, so I know we can discuss how we can help you. Okay. Any questions? Regarding the problems, we have 2 sections, and in section 1, we found we have the most mistakes in problem 2, 3, and 6. Okay. Section 2, we have the most mistakes from problem 2B. Okay, so we're gonna go over them. Let's move this.
I think one of the big problems was you didn't realize there's one right answer.
What's that?
On the multiple choice, just one that was right. At least I did. I was like,
Oh, I wrote the hints on the blackboard. Did you see that? There are 2. I mean, for most of the problems, there are 2 correct answers, and you should aim for that. So I mean, that's one of the reasons I recommend you to come to take exam in the class, in the classroom, because if one student asks me questions about the exam problem, I will explain to everybody just to make sure it's fair, right? So I mean, number 1 is obvious, right? So I'm not gonna talk about it. Number 2, there are several traps I specially designed here just to check if you really understand the concept well. One trap here is the A vector, the unit vector, is actually pointing outward, not inward, right? So if you really don't understand the concept well, then you can be trapped here. The next is the flux Ni is perpendicular to the surface enclosing the control volume. This is not true, right? Because the control volume is what we pick. It can be arbitrary, right? So which is to say, and for the flux Ni, it's kind of the direction of the flux Ni is not necessarily perpendicular to the control volume, because like I said, the control volume is arbitrary, right? So this is wrong. So that's why we need to do a dot product here, right? The purpose of dot product is to find the part of Ni that is parallel to the unit vector of the control volume, right? And the minus sign here says that the unit vector is actually pointing outward, right? So what we compute here is the net outflow right? And then you have to add a minus sign to just to reflect this whole term reflects the net inflow in your control volume. Okay. So for problem 3, I think it's most of them are pretty obvious. You can find the answers from your lecture notes. I mean, the same here. I deliberately add some trap here just to see if you can tell it. And one trap is for sure, liquids have higher diffusivity than gases. That's not true, right? In a general sense, that's not true. And at the continual level, diffusion tends to create concentration gradient. That's kind of the opposite. Diffusion tends to smooth concentration gradient because we talk about this. Concentration gradient is a driving force for molecular diffusion. As diffusion happens, it smooths out concentration gradient. So you have less concentration gradient, then you have less diffusive flux until at equilibrium, the diffusive flux drops to 0. Right? When you don't have concentration gradient, you don't have the driving force for diffusive flux, and you don't have macroscopic change to the concentration, right? That's when you reach equilibrium. Okay. So the correct answer is B and C. A and D are incorrect. Problem 4, I think most people are able to crack this problem. What we should be aware of here is that I'm trying to use description statement instead of equations to kind of reflect some of the concepts, because in the class I write down equations, right? So you're probably very familiar with equations. But I just want to test if you really understand the equation, right? So here, if I write down JA equals JB, I guess you will be able to tell right away it's incorrect. But if I put it into a statement, maybe it's more difficult, right? So the problem here is that for a binary system, the JA equals minus JB. So the magnitude is the same, but direction is opposite. Okay. C is correct. And then D is that the total mole flux of a component equals to its concentration multiplied by not the average velocity, but by its own total velocity, right? That's kind of the definition. So for this one, the correct answer is A and C. 5 is pretty obvious. I think most of you guys are able to get a right answer. 6 is kind of like difficult because I guess it really requires you have a good understanding of the dot product and also the understanding of the integral. So here, Vz is the velocity, right? The V vector is pointing in the direction that is parallel to these arrows, right? And in this pipe problem, if we just cut the cross section in a random direction, A is the normal direction of this cross-sectional plane, right? So this A vector is not necessarily parallel to the velocity of the fluids, right? In this particular case, it's not. There's an angle. Dot product, again, dot product measures in this case, because A is a unit vector, right? So its magnitude is 1. And the dot product between V and A gives you the, mathematically it's V multiplied by cosine theta, and theta is the angle between V vector and A vector, right? Physically, this tells you the projection of V vector on, if this is V vector, if it's A vector, this tells you the projection of V vector onto the direction of A vector, right? And it's smaller than Vz, that's kind of Z direction velocity. So this is, A is correct, so B is incorrect, right? But if you have if you cut the tube vertically, so that this cross section is perpendicular to the flow direction, in this case, B is correct, A is incorrect, right? Do you see the difference? Now, CD is kind of like also quite confusing here. Although V, in this case, V dot product with A is smaller than VZ, but when you do the integral, right, in this particular case, as you can see, this whole surface, it passes through the whole tube, right? So the cross section really covers the whole cross. I mean, this slice really covers the whole cross section of the tube. So then when you do the integral, then in this case, it doesn't matter how you cut, in which angle do you cut the tube, right? As long as, you know, the cross section cover the whole, I mean, this slice cover the whole cross section of the tube, then the answer will be the same, right? So it will be equals, you know, this 2 pi r multiplied by Vz, and you do integral from 0 to r. Okay, so D is correct, C is incorrect. Questions? Okay, no.
A was
A is correct and D is correct. B, C are incorrect. Okay. So section 2 problem 1, I think this one is everybody's doing this quite well. I mean, in the end, you just need to find the right equation, plug in the numbers, and make sure you do the math correctly, right? So I'm not gonna dive into this until any questions. No, okay. So I think you're good. So number 2. So this is kind of like one of our homework problem. We have this in our homework 1 and 2. So I'm trying to use these homeworks just to, you know, familiarize yourself about how to analyze if you have a random shape. I mean, if you have a tank with some shape, how do you kind of like conceptualize the mass balance, mole balance problem in such a tank, right? So number 1 is that what is the flow rate to maintain the fluid height at HS and not change? So we just need to, you know, in our review section, we'll talk about for this type of problems, you have at least 2 conservation equations you can write down. One is mole conservation, right? And that's derived from the integral mole balance equation in which you have, you know, d and I dt. That is equal to, you know, C V minus C out, V out, right? This is one equation. And other equations, when you have fluid coming in, if you have fluid leaving the tank, then total fluid volume must change, right? If we neglect the mixing effect, right? If we assume that mixing does not cause volume change, then the only source of volume change comes from the difference of the flow rate in and out, right? So we have dV dt equals V in minus V out. Okay. So when you analyze this type of problems, you just need to, you know, first write down these 2 equations, then ask yourself which parameters are known, which are unknown, right? And how can I get the unknowns from the knowns based, you know, given this particular problem? So here, flow rate is if the fluid is at a steady state HS that does not change, that means the volume is also not changing, right? Although volume not changing is not explicitly stated in the problem statement, but you should know that when height doesn't change, volume doesn't change, right? Then we can just set this equation to 0, right? And then now HS is given, right? So you can just write down V in, you know, equals V out. And for this type of problem, we know the outlet flow rate is proportional to, you know, the velocity multiplied by the cross-sectional area, which is 2 pi r. Oh, sorry, not 2 pi, pi r squared. Multiplied by, I think this is 2 pi, 2 GHS, right? That's pretty straightforward. Questions? Okay. I think what makes, what is more difficult is the second problem. I guess maybe you are confused about what you need to get, right? But next time in the exam, if you don't understand the problem, please ask, right? So some of the statement seems to be repetitive. And the point of that, when I wrote this exam, the point of me trying to write repetitive statement is trying to make sure you really understand what I want, right? So now the tank is being filled with pure water at a above calculated flow rate. That means, the fluid, the fluid needs well stay at a height of HS and not change. So filled with pure water means there's no component A in your tank before you start to fill this stream of CE, right? And again, I emphasize the total volume of fluid in the tank does not change, right? That is just a repetitive statement that is consistent with the first statement, right? Assuming the tank is well mixed, that means that you don't have to consider the concentration inhomogeneity in the tank. You can assume you use one parameter, CA, you can describe the concentration in the tank. Initial concentration of A in the tank is CA 0, and that's the initial condition. Please write down the ordinary differential equation to correlate the correct concentration of A in the tank with other parameters, right? Now, for this type of problems, again, you write down the equation, right? We know to describe the mole balance of this tank, you start from D and I. Sorry. Let's go back. Okay, so you start from D. Okay, so seems like it's quite slow. I'm gonna go to the old style. So the technology doesn't always work out, right? So we have to go back to the old style. In this case, you go back to start from the definition. You have dNA over dt, right? And that's kind of more change in the tank, right? Now we have incoming flow with known flow rate and with no concentration of Ca, that's Ce, right? Then we have a leaving stream whose concentration is Ca, right? Because we assume it's well mixed, so the leaving stream will carry a concentration of Ca, right? Multiply by V out. Okay. Now, say Na equals, because Na equals Ca multiplied by V, right? Then dNA dt is this term, dCA V dt. And because this is like a product, we can break them down into two components. You have dCA dt multiplied by V plus Ca dV dt, right? Because the volume of the tank is not changing, and the volume of the liquid in the tank is not changing. This term drops out. Okay, we have only this term. If you plug it back, you have to make some rearrangement. You have dCA dt equals Just divide V to the right, you know. C, V, V minus C, V out. Okay. Now, the problem asks us to write down the explicit form of dCA dt with other parameters C, HS, R, theta, right? So the dCA dt needs to be a function of C, H, R, and C. So kind of like we have to get rid of V, get rid of V in, and get rid of V out. Yes.
Why did we not divide V by every term?
What's that?
Why did we not divide all the terms by V?
Oh, sorry. Yeah, you're right.
Okay.
Okay. Then we just need to find out how to relate V in, V out with these. Then we're done. Right, then V in is V. Well, V in equals V out. Right, as we learned in the first problem, that is square 2G HS, right? And then you just define our V. And we know from the homework problem, you can do the integral from R to RS. Then dr is going to be pi R squared GH. Okay. Do I need you to derive this? I mean, this is your homework problem. I don't think I need to do this, redo this. Right? Does anybody need me to do this? If no, we can just conclude here. No? Yes.
Oh, are we gonna post a solution to get them back?
No. So you can go talk to the TA to check your grade if you have any questions about the grade. And if you have questions how it's graded, then you can go talk to the TA. Yes.
I'm just curious, would that have been an acceptable answer for me, or would you have expected us to? Because like that is in terms of.
Yeah, you need to convert this into this form. That's your homework problem. If you know how to crack your homework problem. Yes.
Our next math exam is week on Friday. Friday, 2 weeks.
Next exam.
Yeah,
Yes.
next exam.
Yes.
My boyfriend is skiing in a national race, so I'm leaving Thursday and coming back on Monday. Is it possible I could take it the Wednesday or the Wednesday?
So you're going out for a race?
Yeah, ski race.
Okay, okay, sure. Send me a message. I will describe your situation. I will forward this to the TA.
Okay.
They will arrange an exam for you. Probably after Friday.
After, okay,
After Friday.
perfect. I could take it the Monday because we're coming back we're leaving Thursday and we're coming back on Monday. So
Okay.
I could take it the Wednesday before or the Wednesday after. I'll let you know in the email. I just put it-
So yes, just send me this message. The TA will reach out to you. Then they will schedule an exam with you. Most likely after that Friday.
Okay.
You come back, you can do the exam.
Thank you so much.
Okay, no problem.
Thank you. I don't know why I talk about it. I've never had a freaking. By the time I got.
Yeah, no problem.
one